The Misfit House. Tom had always been fascinated by building things, so one day he decided to craft a toy house from scratch. Armed with a ruler, some wood panels, and plenty of enthusiasm, he set to work. Carefully, he measured and cut the panels, using a ruler marked in centimeters to guide him. After hours of sawing, sanding, and assembling, his creation finally stood before him. But something was terribly wrong. The walls leaned awkwardly. The doors were too small, and the windows were oddly shaped. Instead of the cozy little house he imagined, Tom had created a bizarre, lopsided structure. A real Frankenhouse. Frustrated, he stared at his creation, scratching his head. "I measured everything," he exclaimed. "Why did it turn out like this?" Seeking answers, he turned to his friend Judy, a meticulous crafter herself. Judy inspected the house and then his tools. With a knowing smile, she held up his ruler. "Tom, this ruler only has centimeter markings. That's fine for some things, but when precision matters, you need a ruler with millimeter markings." Tom blinked. Millimeters? Does that really make such a big difference? "It absolutely does," Judy replied. "The smaller the unit, the more precise your measurements." That's the secret to getting everything to fit perfectly. Determined to set things right, Tom followed her advice. He got a new ruler with millimeter markings and started over. This time, he worked more carefully, double-checking every measurement. When he finished, the new toy house stood tall and proud. The walls were straight, the doors fit perfectly, and the windows were just the right size. Tom beamed at his success. It's amazing how one small detail can make all the difference. Judy nodded. "That's the magic of precision, Tom."
Do you know the difference between accuracy and precision? Exact numbers. Some numbers used in chemistry are exact. 1. Define numbers. Define numbers are exact because they are assigned specific values. For example, the numbers in the relationships 1 dozen equals 12, 1 inch equals 2.54 centimeters, and 1 minute equals 60 seconds are exact. 2. Counting or cardinal numbers. Counting numbers are exact because they represent quantities that can be counted without error. For example, the number of students attending a class today is a counting number. For these numbers, there is no uncertainty in their values. Inexact numbers. Numbers obtained by measurement or from observation, however, always have some degree of uncertainty. Accuracy describes how close the average of a set of measurements is to the true or accepted value. The closer the average, the more accurate the measurements. However, accuracy alone can be misleading. For instance, suppose the true value is 1.0 and 3 measurements yield 0.5, 0.8, and 1.7. The average of these measurements is 0.5 plus 0.8 plus 1.7 divided by 3 equals 3.0 divided by 3 is equal to 1.0. This matches the true value exactly, making the measurements appear accurate. But the wide variations between the numbers indicate a lack of consistency in the measurements. Precision refers to how closely individual measurements agree with one another. In the example above, the measurements have poor precision. Ideally, good measurements should be both accurate and precise. Using instruments with finer scales can help improve precision.
All right, class, let's do something simple but fun. Measure the length of this pencil. Just eyeball it if you must, but give me a number.
It's 11.3.
Okay, 11.3. Anyone else?
I think it's 11.4.
Interesting. And you, Jake?
I would say it's 11.2.
So, all three of you agree the pencil is 11 plus something. But you're disagreeing on the something, huh? Caleb, let's start with you. Did you just throw that number out of thin air?
No way. I'm serious. I measured carefully.
Lisa, do you stand by your number?
Absolutely. I'm sticking with 11.4.
All right. And Jake, I see you're just as sure of your 11.2. You know what I think? The numbers you came up with, the 11, the exact part, and that last little digit you're all so passionate about, they mean something to each of you. They're not just numbers. They are significant numbers. And in science, when numbers matter this much, we call the digits significant.
Significant figures. There is always some uncertainty in the last digit reported for any measured quantity. For example, if we measure the volume shown in the figure, the meniscus appears to lie between the 6.8 milliliters and 6.9 milliliters marks, so we may estimate the height to be 6.82 milliliters. We usually report the precision of a number by writing an appropriate number of significant figures. All digits of a measured quantity, including the uncertain one, are called significant figures. In the above example, the number of significant figures is 3, 2 of which are certain, 6 and 8, and one that is somewhat uncertain, 2. Here are rules to determine the number of significant figures in a reported measurement. Non-zero digits are always significant, no matter where they occur. Zeros can be used either as part of the measured value or merely to locate the decimal point. They may or may not be significant. Zeros at the beginning of a number are not significant. They are used simply to indicate the position of the decimal point. Zeros between non-zero digits are always significant. Zeros at the end of a number and to the right of the decimal point are significant. A zero at the end of a number that does not have the decimal point may or may not be significant. In such cases, it is normally assumed that the zeros are not significant. So, only 3, 7, 0, 8 are significant figures. To indicate the last zeros are significant, place a decimal point at the end, like 37080 point. The following table summarizes the significant figures in the numbers we just considered. The digits that are significant are highlighted. Scientific notation. In chemistry, the numbers we deal with are often either extremely large or extremely small. Such numbers are conveniently expressed in the form c times 10 to the n. Here, c is called the coefficient or significand and is a number between 1 and 10. N is an integer, positive or negative, called the exponent. For example, the decimal number 3,700,000 can be written in scientific notation as 3.7 times 10 to the sixth power. Another example is 0.000307, which in scientific notation is 3.07 times 10 to the negative fourth power. An added advantage of using scientific notation is that it allows us to express all significant figures in the coefficient unambiguously. For instance, consider the number 1,000. In its decimal form, we assume that the 3 zeros are not significant digits. However, if we want to specify that the first 2 digits are significant, we can write it as 1.0 times 10 to the 3. Quite convenient, isn't it?